So every load that we've looked at so far has been based on that we have a constant temperature application. What happens when we change the temperature? And this is where you're going to see a lot of this statically indeterminate stuff. A lot of the problems are actually just temperature-based ones because we have something that is set and it's completely fine, and then we heat it up or cool it down and things change. So let's take a look at what happens from thermal stresses. So let's bust out some thermodynamics work back from physics 2 or 3 class. Forget which one you take. And let's talk a little bit about how we can calculate out the amount of deflection with that. And the first thing that we need to talk about is the coefficient of thermal expansion. So coefficient of thermal expansion is a material property. It tells us how much a property will expand and contract due to temperature. So coefficient of thermal expansion, let's continue your classical Greek education. Lowercase alpha. At some point you'll take a fluid mechanics, fluid dynamics, you'll hear about angle of attack, that's also alpha, but in our case alpha is just the coefficient of thermal expansion. And coefficient of thermal expansion will be in units of inverted temperature. So you're going to be looking at stuff per degree Fahrenheit per degree Celsius. And it's basically how far something will stretch or contract due to temperature. So what you do is you sit there and you go, okay, well, alpha times the change in temperature will tell you how much expansion or contraction that you have. So if you want to find out how much deformation that you have, because if you think about it, alpha is going to be per unit temperature, your change in temperature will be times some temperature. It really gives you a percentage. And if you multiply that by the original length, that will give you your deformation. I'll give you a special kind of deformation. We're going to call it delta sub T. So we're going to call that the thermal deformation. So this is how you would figure out exactly how far a material expands or contracts depending on its material properties. So I guess we can box this one because I know undergrads love their boxes for equations. And so basically, how do you calculate out delta T? Well, delta T is T2 minus T1. So if you're increasing in temperature, T2 minus T1 is going to be a positive number. And so that will give you a positive expansion. If it's a negative, if it's a T1 is higher than T2, you're going to end up with a negative number. And so things will contract. So it'll get smaller. So we can sit there and take a look at things and define thermal strain, because what is our definition of strain? Strain is just nothing more than the deflection over the initial length. So if I take that thermal deflection divided by the initial length, I'm just going to take this here, alpha delta T times L, divide that by initial length is L, and so those cancel out. And so our thermal strain is nothing more than just alpha delta T. Which, once again, as when we talked about it a little bit earlier, we should have been able to sit there and go, oh, that's right. It's just because it's unitless. So 1 over centigrade times centigrade, or 1 over Fahrenheit times Fahrenheit, is just going to give you this unitless parameter. And the way this works into what we've been doing is the only way to develop a thermal stress into a part is to put it in a statically indeterminate situation. Because typically if I have a bar here and I set it on a hard surface and I raise it 50 degrees, what happens? Well, it's going to expand. It's going to get bigger. How much stress have I put in the bar? None. Because it just gets bigger. There's nothing that's going to be a problem. And if I go and I sit there and I put, okay, well, I want to put a wall here now, and I let it get hot, what happens? Well, it expands that way because it's not going to expand the other way because it's bound. There's going to be no stress in it. There's going to be no internal force in it. How do I get an internal force in it? Now I put a wall there. Now I heat it up. It can't expand. It tries to expand, but it can't. And so as it tries to expand, now what you have is you have reaction forces that are going to be created. They're going to push back on the other sides. And so now you're going to develop some kind of internal force in there. Now we have an internal force that gives us an internal stress. And so thermal expansion problems, these are important because these are things that we will see in real life. This will happen, especially in things like engines, where you have to worry about things like that. Optics. Back in my career, I dealt a lot with thermal expansion in optics. Not so much for the stress, though, which was a concern. I was more worried about the fact that it would shift optics around and change the focus. But we see these thermal problems that pop up constantly when we're dealing with materials.